Hello, I'm Dale Jackson, and today I'll be talking with you about some basic op-amp configurations. We have here an op-amp buffer, a non-inverting op-amp amplifier, and an inverting operational amplifier. So, to derive the expressions that will tell us the relationship functionally between V in and V out, we'll start with our buffer. So, with our buffer, we notice here that V out equals V in, and we also see here that V in, not V in, but V in equals VP. Well, because of an op-amp property here, we have that V in equals VP. So then, since VP equals V in and V in equals V out, we have to have that V out equals V in. So that is the functional relationship that we have here between the voltage in and the voltage out. It just buffers it. So if you want to isolate one stage from the other, it'd be a good idea to use a buffer. It'll help you do that. The input resistance is very high for an op-amp. Ideally it would be infinite, but it's very high for a practical op-amp, and the output resistance of an op-amp is very low. Ideally it would be zero. It would be an ideal voltage source out, but it'll be very low, so we can use a buffer for that purpose. Next, we have our non-inverting operational amplifier here. And so, of course, we have Vn here, this node, and Vp at that node. So if we arbitrarily just assign currents here, and we start from node Vn, and we use KCL, Kirchhoff's current law, then what we'll see is that Vn minus ground over R1 plus Vn minus V out over R2 plus In equals 0. And In itself is 0, so that'll reduce and that'll come out because it's an op-amp property that this current will be very low, and ideally it will be 0 going into the op-amp. And ground, of course, is 0, so that reduces to 0 there. And then so we're left with Vn over R1 plus Vn minus V out over R2 equals 0. Now, again, because of this type of relationship that we have Vn equals Vp, we also notice here that Vp is equal to Vn. And so what we'll do here is we'll back substitute in there, and we'll come up with an expression that says Vn over R1 plus Vn minus V out over R2 equals 0. And so by rearranging this so that we have a relationship of V out in terms of Vn and the resistances R1 and R2, this will be our functional relationship between V in and V out. So next, finally, we'll move on over to our inverting op amp here. And for our inverting op amp, we'll do the same. At Vn, we're going to use KCL, and we're going to see that Vn minus Vn over R1 plus Vn minus Vout over R2 plus In equals 0. And of course, In will be very low. Ideally, it will be 0 for an op amp property that we have here. And so that automatically reduces, and we'll take notice here that Vn, of course, with this other op amp property, it's actually called a virtual short, and Vn will be equal to Vp with our virtual short, and Vp is connected to ground, so Vp equals ground, and ground equals 0. So what we have here by substitution is 0 minus Vn over R1 plus 0 minus Vout over R2 equals 0. And then by rearranging this equation, and putting V out in terms of Vn and our two resistances, we have so V out in terms of our two resistances, and Vn is this functional relationship. So those are our three functional relationships for our buffer. V out is going to be equal to Vn. For our non-inverting amplifier, Vn is going to be multiplied or scaled up or scaled down. It's going to be scaled by the ratio of R2 to R1, and it's also going to have 1 added to it. And R2 to for our inverting amplifier, it's going to be a negative R2 to R1 scalar. So in other words, this negative shows us inversion. So if R2 and R1 have the same value, and we put in like 1 volt here, we'll have a negative 1 volt on the out. So it'll just invert whatever we have. Or if we put a negative 1 here, we'll have a positive 1 there. And so so what we can do now is we can take a look at this on a simulator and use a couple of values in order to see the effects of these types of relationships here and plot them and graph them. Okay, so what we have here is we have our 3 basic operational amplifier configurations: our buffer, our non-inverting amp, and our inverting amp. And so what we'll do is we'll verify the functional relationships of each one of those from what we derived on the board. And so for our buffer, V out should equal Vn without any scalar. Let's simulate that and take a look. Vn, which is the red, V out is the aqua blue, Vn is set to be 1 volt peak. The scaling for the input channel is 2 volts, so 2 volts per that one division, and it's half of that division. Well, half of 2 is 1, so we can see here 999 millivolts, that's 1 volt, and same thing for our output, 998 millivolts, that's a volt. If we were to scale down the volt per division for our input, we'll see that it overlaps.
which is why it's convenient in this case to use a scaling of 2 volts per division. And so that verifies the relationship that our output equals our input without any modification. And that is the function of our buffer. So for our non-inverting amp, what we'll do is we'll simulate that and take a look. Well, what we can see here is that they're both scaled the same, and so they're 1 volt per division. We have 1 volt peak for our input, which is our red, and our output, which is our aqua blue, is scaled up to be a version of Vn but times 3. So the values that we've chosen here for R2 and R1 are 2K and 1K. So our functional relationship is Vn times R2 over R1 plus 1 is going to be equal to V out. And so 2K over 1K is 2, and then 2 plus 1 is 3. So 3 times Vn equals V out, which is exactly what we see here. We can even use our cursors to approximate things and take a look at it there. So we see 999 for our input channel, 999 millivolts, which is 1 volt for our input channel, and then we see 2.99 volts for our output aqua blue channel here, and so that's approximately 3 volts. So we've just verified our functional relationship for our non-inverting amp. And then last here, for our inverting amp, we have R4 equal to 2K and R3 equal to 1K. Well, negative R4 divided by R3 times Vn equals V out. So if we have 2K for our R4, 2K over our R3, which is 1K, 2K over 1K is 2. So, and then we have our negative in front. Negative 2 times Vn should equal V out that we have here on this oscilloscope here. And so what we expect to see is an inverted version of Vn times 2 scaled up by 2 to be V out. And so if we would take a look at our simulation here, we can see that Vn is our red, V out is our aqua blue. They're both to scale as 1 volt per division, and we can see that just by using the cursors to approximate, we can see that when Vn is 1 volt, V out is negative 2 volts, and we can see that when Vn is negative 1 volt, V out is 2 volts. So that has just verified our functional relationship. You can see that V out is a scaled up version of Vn, but it's inverted, and it's scaled up by 2 in this example, based upon the choices the values that we've chose for our R4 and R3 resistors here. So that will do it for our simulation part of this video.
So I hope this video was helpful to you. Thank you for watching, and have a nice day.